Morning, everybody. Welcome back to Calc 2. Plan for today is we are going to try to finish off Standard 11, talking a little bit more about series, including a couple of tests today for determining how do you determine whether or not one of these infinite sums converges or diverges. So, got my usual office hours over the next few days, 11 to 12 and 1 to 2. I posted a new homework assignment, homework 15, to be due Friday. We'll have a quiz Wednesday over Standard 11, and put it on your calendars now. Not this coming Friday. Since for coming Friday is Good Friday, we'll have class off. But Friday, a week from this Friday, we will have our second midterm, which I'm guessing we'll have standards 1 through 12 on it, if I had to guess. Everything up through this standard plus the next one, which we'll tackle over this Wednesday, probably next Wednesday. Yes, Dave?
How many standards do you think we'll get through before the end of the semester? Can we through all of them?
Well, we've already skipped one, so we're not getting through all of them. We'll probably get through about... Let's see, that one's fairly quick. That one's 13. 14, 15, 16. My guess is 17 at this point.
Okay.
And yes, that does mean I'll post update when I have a better sense. I'll post updated. How many masteries do you need for each letter grade when the time comes?
Sure. And if we miss some of them, will it harm us in Calc 3 if we miss the end? Should we go like?
Oh, it'll be the travesty if you miss anything. Not particularly. The two things I'm a little worried we're not going to get to are polar and parametric coordinates. And Calc 3 kind of starts off with a review of those, so I don't think it would be super harmful for this day. Anybody else? Okay, in that case, several people are asked one day to test the following hypothesis, that all odd numbers greater than 1 are prime numbers. So mathematician goes first. They reason 3 is prime, 5 is prime, 7 is prime, 9 is not prime, therefore the hypothesis is false. The physicist says 3 is prime, 5 is prime, 7 is prime, 9 is not prime, 11 is prime, 13 is prime, hence 5 out of 6 experiments support the hypothesis. Clearly it must be true. The computer science student reading the output from the screen says 3 is prime, 3 is prime, 3 is prime, 3 is prime. They need to work on their code. The biologist says 3 is prime, 5 is prime, 7 is prime, 9 is... more research is needed. The psychologist claims 3 is prime, 5 is prime, 7 is prime, 9 is prime, but tries to suppress it. And finally, the politician says some numbers are prime, but the goal is to create a kinder, gentler society where all numbers are prime. And with that, let's get going. So last time we started talking about what it means to add up the terms in an infinite series. If we have A1 plus A2 plus A3 plus A4 going on forever. And the idea behind determining whether or not that infinite sum comes out to a finite number or goes to, say, like infinity or does something weird, is we look at its sequence of nth partial sums, where, in general, we would say where we would say something like S sub 1 is the first term, S sub 2 is the sum of the first 2 terms, S sub 3 is the sum of the first 3 terms. And then we look at the sequence of nth partial sums and see does that sequence of partial sums converge or diverge. And if it converges, then we say the series converges to whatever that limit is. And if the sequence of partial sums diverges, then we say that the overall series is going to diverge as well. And just as a quick sort of recap from what we were doing towards the end of class on Friday, if you wanted to take, for instance, the sum from, let's say, n equals 1 to infinity of 1/2 to the n, actually I forget, did we start at 1 or 0? We started at 1. Which is, if we're looking at the infinite sum, 1/2 plus 1/4 plus 1/8 plus 1/16 going on forever. The key idea behind this is we can look at the partial sums of this series. Where our first partial sum, S1, is just going to be the first term that we're adding up. In this case, a half. S2 is going to be the sum of the first two terms, 1/2 plus 1/4, giving us 3/4. S3 is going to be the sum of the first three terms, 1/2 plus 1/4 plus 1/8, giving us 7/8, and so on. And so then if we start looking at our sequence of nth partial sums, we got something like a half, the first, we got like S1, S2, S3, S4, etc., which as a sequence would look like the sequence 1/2, 3/4, 7/8, 15/16, and so on. And what did we say about the sequence of nth partial sums? 1/2, 3/4, 7/8, 15/16, etc., Is this sequence going to converge to anything, or is that going to be a divergent sequence? Jonah?
So it converges to 1?
Yeah. The sequence of nth partial sums converges to 1. Which means that our initial series is also going to converge to 1. 1/2 plus 1/4 plus 1/8 plus 1/16, etc., converges to 1. So did y'all ever hear the one about an infinite group of mathematicians walks into a bar? An infinite number of mathematicians walks into a bar. First one of the mathematicians goes up to the bartender and says, I'm not that thirsty, I just want half a beer. Second mathematician goes up and says, I'm only half as thirsty as that guy was, I'll only take a quarter of a beer. Third mathematician walks to the bar and says, I'm only as half as thirsty as the last guy was, I'll only take 1/8 of a beer. At this point, the bartender looks at this infinite line of mathematicians and said, all right, let me get this straight. Are all of you only half as thirsty as the guy in front of you? They'll go, yeah, uh-huh. Bartender pours a single beer, puts it on the counter, walks away. Because 1/2 plus 1/4 plus 1/8, etc., converges to 1. And that's where we left off last time. Any questions, comments, concerns? So, if we were to look at these individual terms, 1/2, 1/4, 1/8, 1/16, if we were to try and write out each of these terms as a sequence, where each term is, say, the same constant multiple of the term that's before it, in this case, each term in this sequence is 1/2 times the term that came before it in the sequence. What type of sequence did we call this back in Standard 10? Anybody remember? Started with the letter G. G? Yeah, we call this a geometric sequence. Back in Standard 10, where each term is like a same constant multiple of the term that came before it, in this case 1/2. So what I want to do today is I want to focus on looking at a particular type of series called a geometric series, where in essence what we're going to be doing in a geometric series is adding up all of the individual terms in a geometric sequence. And what I want to do is to see if we can notice any patterns of determining when a geometric series is going to converge or diverge. So let's do that. So we're going to define a geometric series with ratio r is going to be a series of the form sum from k equals 0 to infinity of c times r to the k. So in other words, a series that's of the form, you start off with some constant c, but then you add to that constant times ratio r plus cr squared plus cr cubed plus cr to the fourth, etc., going out forever. So like in this case, we could say this example was of a geometric series where our first term was c equals a half, and our ratio of successive terms, our r, what we need to multiply to get from one term in our sum to the next. Surprise, that's also a half. And the idea behind a geometric series is we actually can come up with a formula for determining whether or not a series that looks like this is going to converge or diverge. And if it converges, we can determine what it's going to converge to. So let's see if we can do that. When does a geometric series converge? And if it does, and if so, to what? So let's take a look-see. So the first thing I'm going to do is if we have a series that looks like this, c times r to the k, c plus c times r plus cr squared plus cr cubed. Be nice to have a general, be nice if we could somehow factor the c out of this. And in general, you can factor out the constant c and write c times 1 plus r squared plus r cubed going on forever. To say that's just going to be c times the sum from k equals 0 to infinity of r to the k. So in other words, we can make our lives a little bit easier by just starting by factoring out our constant multiple c out in front of the entire sum. And so what I want to do, or what I propose that we do, is we're going to look at this series right here. Just the sum from k equals 0 to infinity of r to the k power. Which is going to be 1 plus r squared plus r cubed plus dot dot dot. Because if we know whether that series converges or diverges, that'll tell us whether this whole series is going to converge or diverge. Any questions or comments thus far before we get into the nitty-gritty? Alrighty, so Joy, I see you smiling over there. If we look at this series right here, what's going to be its first partial sum? Yeah, just the first term that we're adding up in the series, which is going to be 1 in this case. So, Reagan, how about our second partial sum? If we added up just the first two terms in this infinite sum. It's not going to be 2. if we look at what we're adding up here, our first term is 1. What's the second term that we're adding? Yeah. So what's the sum of 1 and r?
1 plus r.
1 plus r. Indeed. All right, Jonah, how about our third partial sum?
Should be 1 plus r squared.
1 plus r squared. All right, James, can you give me a formula for our nth partial sum?
1 plus r squared plus r cubed plus dot 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 plus r to the n.
Plus r to the n?
Yeah.
Incorrect. Baby?
Is it r to the n minus 1?
Yeah. Notice that if we're adding up the first n terms, S2 doesn't end with r squared. It actually ends up with the power of r before r squared. S3 ends up with the power of r before r cubed. So the nth partial sum is actually going to end with r to the n minus 1, not r to the n. My goodness. Please excuse me for picking on James. I love picking on James. So, it'd be nice if we had a nicer formula for this. Specifically, I would love it if we had a way to write out our nth partial sum in a way that didn't have to include a plus dot 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 in the middle. Turns out, there is a sneaky way that you can do that if you're clever about it. So, this gives us our formula for S sub n. What would we get if we took a formula for r times S sub n? Nothing?
We get r plus s squared plus dot 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 plus r to the n.
Yeah, we get the same thing, but every term is getting multiplied by r. So we're going to start adding up powers of r again, except this time we're going to start with r and end up with r to the power of n when we take this whole expression s sub n and we multiply by r. So what I want to do now is I'm going to take these two expressions, r times s sub n and plain old vanilla s sub n, and I want to subtract them. I want to take r times s sub n and subtract from that s sub n. Which if we do that, we're going to be getting r plus r squared plus r cubed plus r to the n minus 1 plus r to the n. And we're going to be subtracting 1 plus r squared plus r cubed up to r to the n minus 1. Is there anything we could put a swoosh swoosh on here? Jonah?
It's the r squared and r cubed, and also the r to the n minus 1.
Yeah, we have an r minus an r. Swoosh swoosh, those cancel out. The r squared terms are going to cancel out. The r cubed terms are going to cancel out.
The r to the n minus 1.
R to the n minus 1 terms are going to cancel out. In fact, everything in the dot dot dots is going to cancel out. So Jonah, what does that leave us with?
R to the n minus 1.
Turns out, if we take r times s sub n and subtract off s sub n, what we're going to be left with is we're still going to have a positive r to the n, and we're still going to have a minus 1. But literally every other term in this expression is going to cancel out. So, what does that tell us? Well, it's going to tell us that r to the n minus 1 is equal to r times s sub n minus s sub n. Maria, is there anything we can factor out of r times s sub n minus s sub n?
S sub n,
Yeah. So if we factor out an s sub n, what's that going to leave us with?
or minus one.
You got it. So it turns out r to the n minus 1 is equal to s sub n times r minus 1. And if we solve that equation for s sub n, what we're going to end up with is a general formula for the nth partial sum of our geometric series up there. It turns out that 1 plus r squared plus r cubed all the way up to plus r to the n minus 1 is actually going to simplify quite nicely for us into r to the n minus 1 divided by r minus 1. As long as r is not equal to 1. Because if r is equal to 1, then we're dividing by 0, and that leads to sad times. So this is specific for this series right here. It's not a formula that's going to hold true in general. Everyone do it okay so far? Groovy. So with that kind of gives us a nice way to take our nth partial sum formula down here, which is a little bit difficult to work with because it has a bunch of terms in it. In fact, it has n terms and has this big plus dot 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 in the middle. And it's trying to instead of taking a limit as n goes to infinity of this expression, which we would normally have to do if we wanted to see whether the series up here converges or diverges. Instead of taking a limit as n goes to infinity of this expression, we could take a limit as n goes to infinity instead of this expression. R to the n minus 1 all over r minus 1. So if we do that, well, Emerson, how many, we have 4 different terms up here, r to the n, 1, r, and 1. How many of those terms are going to be impacted as n goes to infinity? So in other words,
Only R to the n.
yeah, only r to the n. Negative 1 and r are both constants as far as r is concerned, or as far as n is concerned, excuse me. So we could write this if we want as being the limit as n goes to infinity of r to the nth power minus 1 all over r minus 1. And the only thing we really need to do is, in finding out this overall limit, is just looking at limit as n goes to infinity of r to the n. Okay? So, what do we know about limit as n goes to infinity of r to the n? Specifically, we talked about this back in Standard 10. When did this limit come out to a finite number? And when did this limit, say, did not exist or went off to infinity or something? Aiden?
If it is less than or equal to 1,
R less than or equal to 1?
Yeah.
All values less than or equal to 1?
I believe so.
Including like R equals negative 10?
Oh, sorry, fraction. So between equal, what includes 0? Equal to 0, including 0 and between 1 as well. Between that range.
Like that?
Yeah.
What about negative 1/2?
That's not negative 1/2.
But would negative 1/2 to the end just be like converging to 0 as sort of having smaller and smaller oscillations?
Okay, negative 1, between negative 1 and 1. There you go.
Between negative 1 and 1. Okay? Are we including negative 1 and 1 in that?
Yes.
So if I were to give you negative 1 to the n, which is the sequence negative 1, 1, negative 1, 1, negative 1, 1, negative 1, 1, you're saying that sequence converges?
No. It doesn't converge.
Would you like to amend your answer for the 5th time?
Yes.
Approximately. Okay. Gates isn't the only one I enjoy making. I enjoy poking fun at sometimes.
It's not including negative ones.
Including 1?
Yes.
Alright, I finally agree. Yeah, so we know that the geometric sequence converges if r is between -1 and 1, including 1, not including -1. So we know this expression right here, we can say converges if r is between -1 and 1, and diverges if r is less than or equal to -1 or r is greater than 1. So what does that tell us about our S sub n? Thus, we can say that S sub n is going to diverge if r is less than or equal to -1 or r is greater than 1 and converges to, let's say, and converges if -1 is less than r is less than 1 to what? If r is between -1 and 1, Jonah, you look like you had something you wanted to say about this earlier. What does this actually converge to? So if I were to give you like a half and say, look at the sequence, a half, a fourth, an eighth, a 16th,
To 0?
it's going to converge to 0. So this actually converges to 0 if r is between -1 and 1. Technically it converges to 1 if r is at 1 itself. Otherwise it's going to diverge. So it converges if r is between -1 and 1 to 0 minus 1 over r minus 1, which is the same as -1 over r minus 1. And that often kind of gets rewritten by multiplying top and bottom by -1 as 1 over 1 minus r. You get questions or comments? Yes, Jonah?
No, nothing.
Anyone hasn't noticed, Jonah has this habit in class, he'll like randomly start giggling and leave me wondering why.
Sorry.
I'm very self-conscious, so if he's laughing at something and I don't know what it is, I assume he's laughing at me.
Yep.
But wait, are we missing something? What if r is equal to 1? Or not r, also all of these r's should be n's, I just realized. Well, that's embarrassing. Is that what you were laughing at?
No.
Including all of these r's. Oops. That's what happens when you have too many variables floating around the problems. Sometimes you start getting them mixed up a little bit. Okay, if n is less than or equal to -1, or if n is greater than 1, this series is going to diverge, but it's going to converge if n is between -1 and 1 to 1 over 1 minus r. On the other hand, if n is equal to 1, if n is equal to 1, we can't use this formula, because that formula only works in the case where n is something other than 1. So if n is equal to 1, then our sum becomes the sum from k equals 0 to infinity of r is equal. if r is equal to 1, dang it, now I'm doing it again, but backwards. If r is equal to 1, then we end up with a sum of 1 to the k, which becomes 1 plus 1 plus 1 plus 1 plus 1 over and over. And Sarah, what can you say about this series? Is it going to converge or diverge? Is that infinite sum going to approach some finite number, or is it going to go off to a plus or minus infinity?
It diverges.
Yeah, it's going to diverge. It's going to shoot off towards infinity, so to speak. So what's our upshot here? We're taking a limit as n goes to infinity. Gosh darn it, I was right the first time. Okay, look, you know how you all reach a point this semester where you're tired? Someone made me, I've second guessed myself, just like how many of you second guess yourselves on quizzes and exams, and Aiden not being very confident in when the geometric sequence converges. I'm doing that to myself now. I was right the first time. This converges if r is between -1 and 1. Diverges if r is less than -1 or r is greater than 1. Okay, I'm feeling good about this time. I apologize for all the confusion. I promise you I do know what I'm talking about. I'm a mathematician, and that makes me a professional. Alright, so what's our upshot here? So the lesson from this is that you should be careful and don't be afraid to move slowly through a problem instead of trying to go too quickly. And the second lesson is that if we were to take a sum from r equals 0 to infinity of c times, not r equals 0, k equals 0, of c times r to the k, which is going to be c plus c times r plus cr squared plus cr cubed, etc., etc. We said before that that's going to be the same as taking c times sum from k equals 0 to infinity of r to the k. We have now determined for which values of r that series is going to converge versus diverge. This is going to converge to c times 1 over 1 minus r, which is the same as c over 1 minus r, if r is strictly between -1 and 1 and diverges otherwise. Okay. Questions or comments before we start looking at some examples of putting this into practice? All right, let's do some examples then, before I set you all loose on a few of your own. So, let's take a look-see. Let's say we had a sum from n equals 0 to infinity of 2/5 to the nth power, which is going to be the same as taking 1 plus 2/5 plus 2/5 squared plus 2/5 cubed, etc., etc., going on forever. We could do the same thing that we did with the 1/2 sequence at the start of class. Actually start writing out individual partial sums, see if we notice a pattern in the partial sums and whether or not they converge. Or, we could be sneaky about it and use this formula that we just found. Because if you notice, this is a geometric series right here. What's our R value in this series? So in other words, to get from one term in our sum to the next term, what are we multiplying by each time? Katie?
This?
Yeah. We're gonna get that R is 2/5. How about our C value? Where if you remember, our C value is just the first term in the sum. James?
It's just one.
Yeah, first term in our sum, we're starting with C equals 1. And according to the test we just did, we know the series is going to converge if our ratio R is between -1 and 1, and is going to diverge otherwise. So, Nolan, if we look at our R value, 2/5, is that between -1 and 1?
Yeah.
So is the series going to converge or diverge? It's going to converge, yeah. Which converges. Since we have a value of R that's between -1 and 1. And what does it converge to? Well, according to that formula, it's going to converge to C divided by 1 minus R. Which in this case will be 1 over 1 minus 2/5. So let's see if we can simplify this a little bit. 1 minus 2/5. Nathan, how can we simplify 1 minus 2/5?
3/5.
Yeah, 1 is equal to 5/5. So if we subtract off 2/5 from that, we'll get 1 divided by 3/5. Joanna, how can we simplify 1 divided by 3/5?
Can't you just times 1 by 3/5, so then it would just be 3/5.
If we were taking 1 times 3/5, we could, but we want to take 1 divided by 3/5 instead of times 3/5. So how do we, excuse me.
Sorry, it'd be 5/3.
Ah, yeah, because you could, yeah, so the idea here is when you're dividing by a fraction, you can multiply instead by its reciprocal. And it turns out this series is going to converge to 5/3, which is 1 2/3, or 1.6 repeating. So if you were to look at the series, so this is 1, this is 0.4, this is 4/25, so that's 0.16, etc., going on forever. That's going to converge to 1 2/3, it turns out, according to this geometric series formula. Any questions or comments about what we did there? This one's not in the packet. What would you say if I gave you the same series, but flipped it over and said sum from 0 to infinity of 5/2 to the power of n? Which would be 1 plus 5/2 plus 5/2 squared plus 5/2 cubed, and so on. Yes, Jonah?
It would be divergent.
It's divergent. How do you know?
Because 5 halves is greater than 1.
Ah, so it's a geometric series where our R value, our ratio, is greater than 1 because 5 halves is greater than 1?
Yep.
Yep. It is a geometric series with R is equal to 5 halves, which is greater than 1, so the series diverges. But Jonah, why would we say it diverges? Couldn't we just plug in, C is going to be 1 again, couldn't we just plug in R equals 5 halves and get a nice number for using this formula right here?
No.
We couldn't? Why not? Why can't we just take 1 over 1 minus 5 halves, which comes out to 1 over negative 3 halves, and just say, hey, the series converges to negative 2/3.
Well, does it fulfill the requirements? And if you actually did the question where you labeled out all the possibilities, or you added up all of the outcomes, then you would get it going to infinity.
Yeah, it doesn't really make sense to say, oh, if we take 1 and then we add 5 halves to that, and then we add 5 halves squared to that. If we start looking at partial sums, our partial sums are always going to be positive. How can that sequence of positive partial sums possibly converge to negative 2/3? It can't. So even though we can plug 5 halves into this formula and get an output number that makes sense, we only use this formula in the case where R is between negative 1 and positive 1. If we try plugging in our value of R into this formula where R is something that's greater than 1 or less than negative 1, we could get a number here, but it's not going to be a number that makes sense. Questions or comments? Okay, let's look at a couple more. I'm not going to set you loose quite yet. How about this next one? Sum from j equals 0 to infinity of 2 times 3 to the negative j. Which if we write that out will give us 2 plus 2 times 3 to the negative 1 plus 2 times 3 to the negative 2 plus 2 times 3 to the negative 3 and so on. First of all, is that even a geometric series? Aiden?
I think it's still a geometric series. We could rewrite our original function or equation the same. 2 times 1/3 the power of j. Just negative.
Yeah. Just treat 3 to the negative j as being 1/3 to the j. Yeah, I think we could do that. Which would give us what? 2 plus 2 over 3 plus 2 over 9 plus 2 over 27, etc., etc. And Rotom, is that going to be convergent geometric series or a divergent geometric series, do you think?
Convergent is R less than 1.
Yeah, it's going to converge. R is equal to 2/3. So we have that our R is between negative 1 and 1. What's it going to converge to, Rotom?
Well, we'll have to plug in the formula.
So what are we plugging into our formula?
So we would have 2 over 1 minus 2/3.
You plug in your C is equal to 2, because C is just the first term in your geometric series. And if we subtract off 2/3 here, we get 2 over 1 minus 2/3, which is going to be what? 2 over 1/3, which is equal to 2 times 3. Is that going to be 6? That doesn't feel right. Phoebe?
Is R supposed to be 1/3?
Yeah, I think R is supposed to be 1/3. Is that what you said, Ronan? I don't think I may have misheard you.
I thought it was a 1/3, but.
Oh, okay, then I think I just misheard you. Yeah, turns out R is going to be 1/3 here. Okay, that number looks too big, which is actually going to give us 2 over 1 minus 1/3, which is 2 over 2/3, which will give us 2 times 3/2, and leave us with 3 as our final answer for what the series is going to converge to. Which makes a little bit more sense. We take 2 and add 2/3 and add 2/9, we're already getting pretty close to 3. If we keep adding these smaller and smaller numbers, we're just going to keep getting closer and closer to 3 as our partial sums keep getting bigger and bigger and bigger. Questions, comments? Okay, let's look at this one. Let's see. What if we take a sum from k equals 2 to infinity of 1/3 raised to the k power? So I'm skipping the one at the bottom of the page for now and moving on to the next one for those of you in the packet. Anna, is this a geometric series?
Yes.
What's going to be its R value?
1/3.
It's a third again. So this is geometric with R equals a third, which means it's going to converge again. This is going to be C over 1 minus R. What's going to be our C value here? Jonah?
Be 1.
It's going to be 1 again? Why is that?
Because it doesn't like show up. It can't be 0 because then it would also be 0. So according to the function, it's gonna be 1.
Oh, it always has to be either 0 or 1?
No. But nothing else is there.
Nothing else is in there?
I guess it could be
So,
1/3. I don't know.
so let's start writing out some terms in this series. So you don't sound super convinced.
Yeah, sorry.
So what would be the first term that in our infinite sum?
1.
I think
No,
it's gonna be one.
minus 2. Never mind, it's 1/9.
Yeah, our first term in our sum, we actually, if you notice, I played a little trick on you all. I actually started at k equals 2 instead of at k equals 0 this time, or j equals 0 or whatever. Our first term is actually going to be 1/3 squared, or 1/9. Using the fact that when it says k equals 2 down here, that means that's the first value that you're plugging in for k in your infinite sum. So, Jonah, has that changed your mind at all on what our c value is? Where c is always the first term in the geometric series?
It'd be 1. So it'd be 1/9.
Yeah,
I didn't
our
realize
c
that.
is actually going to be a 9,
Oh, okay.
owing to the fact that our series starts out at 1/3 quantity squared. So this is the same as 1/9 plus 1/9 times a third plus 1/9 times a third squared, and so on. And then we could take 1/9 divided by, what's that, 1 minus r, so 1 minus a third. Oh boy, compound fractions. Does everybody love compound fractions as much as I do? Devin, do you like compound fractions as much as I do?
Do you not like them?
Not particularly.
Maybe then.
Okay. Alright, so this is going to be 1/9 over 2/3. So Devin, how would you take 1/9 divided by 2/3?
Subtract 1 minus 1/3, that's 1/9 over 2/3, and then just flip it and multiply.
Yeah, so we'll get 1/9 times 3/2, which is going to come out to what?
1/6.
It's going to come out to 3 over 18. Oh, yeah. Why did I want that to be 3 over 27?
Witchcraft.
I don't know, I just love the number 27, y'all. Yeah, it does in fact come out to 1/6. Yeah, you're absolutely right, Devin. Oh man, I'm not on my game today. I'm sorry. Any questions or comments? Let's spice things up a little bit. Let's take a sum. From n equals 0 to infinity of 3 minus 4 to the n over 5 to the n. Holy moly. How do we deal with such a monstrosity? James, any ideas?
So with sums, can you sort of do like the sum and difference rule you can do with integrals, where you can break up the sum of one term plus another term to the sum of the first term plus the sum of the second term?
Ooh, interesting question. The answer is sometimes. But in this case, yes.
Okay. Yeah, because I was thinking maybe you could break it up into 3 over 5, 5 to the n, minus 4 to the n, and 5 to the n.
Yeah, turns out in this case we absolutely can. We'll talk at a future standard about sometimes when you can't. Turns out you can't always when it turns out to be divergent. So this becomes a sum from n equals 0 to infinity of 3 over 5 to the n minus sum from n equals 0 to infinity of 4 to the n over 5 to the n. Are these geometric series? Bethany?
Yeah.
Cool. So for this first series, what's our R value?
Our value could be 1/5.
Yeah, because you can rewrite 3 over 5 to the n as 3 times 1/5 to the n. So this is going to be geometric with R is equal to a fifth. Allie, is this one a geometric series? I'll give you a hint.
Yes.
Yeah, so what's our R value there?
4/5.
Yeah, that one's going to be 4/5. Reagan, we have two geometric series, one where R is equal to 1/5, one where R is equal to 4/5. Are those both going to converge?
Yes.
Because R is between -1 and 1 in both cases? Yep, I like it. So this one is going to converge to what? 3 over 1 minus a fifth? Because if we started plugging in values for n at n equals 0, we would get 3. And for this one, we would get 1 over 1 minus 4/5 using our formula. Which is going to leave us with 3 over 4/5 minus 1 over 1/5. 1 minus 4/5 is 1/5. 1 minus 1/5 is 4/5. Which is going to leave us with what? 3 times 5 over 4 minus 1 times 5 over 1. Which will give us 15/4 minus 5. Which is the same as 15/4 minus 20/4. And I believe we should get an answer in the end of negative 5 over 4. This series comes out to 5. The series on the left comes out to 15/4, and when you subtract the two, we get negative 5/4 as our final answer. Yes, Reagan.
Can you explain where the r equals 1/5 comes from again?
Sure. So that comes from the fact that if you can rewrite 3 over 5 to the end, and that's the same thing as 3 times 1/5 to the power of n. Because multiplying by a fifth is the same as dividing by 5. And then if you just look at what's being raised to the nth power, it's the 1/5 there. And for this one, 4 to the n over 5 to the n, you could just rewrite that using exponent rules as 4/5 to the n to get r equals 4/5 for that one. Questions, comments, concerns? Alright, so one last thing I want to talk about really briefly, kind of finish off the standard, is one more theorem, which can sometimes make your life a lot easier for determining whether or not a series is going to converge or diverge. And this is going to be the divergence test. And what the divergence test says is very simple. It's going to say let a sub n be a sequence such that the limit as n goes to infinity of a sub n is anything other than 0. And it turns out if this limit is anything other than 0, then if we were to take the sum from n equals 1 to infinity and add up all of the terms in our sequence, that series is going to have to be divergent automatically. So what's that saying? A shorthand way of saying this is if the individual terms were adding don't converge to 0, then the sum can't possibly converge to anything at all. So as a quick example, if we wanted to take a series that was something like 1 plus 2/3 plus 2/3 plus 2/3 plus 2/3 plus 2/3 plus 2/3 over and over, Nathan, what can we say about the individual terms we're adding?
Don't convert to zero.
Yeah, they're all well, after the first term at least, they're all 2/3. So we can say the individual terms we're adding converge to 2/3, which is not equal to 0. And if the individual terms we're adding converge to 2/3, which is non-zero, Nathan, what does that tell us about the series?
Don't convert at all.
The series has to be divergent. So this test kind of gives us a nice way to determine if a series diverges really quickly. If you can look at the individual terms you're adding and see, hey, these things that we're adding, they are not converging to 0, that automatically tells you the series as a whole has to fail to diverge. Okay, so here's the scoop. I have more that I would like to say about the divergence test. So we'll talk a little bit more about that on Wednesday before starting Standard 12, which is the integral test. But we can still do a Standard 11 quiz on Wednesday. So for the Standard 11 quiz on Wednesday, what I want you to focus on is looking at the definition of what it means for a series to converge, and being able to look at these sort of geometric series that we played around with for most of class today. Because on Wednesday's quiz, I'll give you a couple series, and using either the definition or the geometric series formula, it'll be up to you all to tell me, does this series converge or diverge? And if it converges, what does it converge to? So that, hope you all have a good one, and I'll see you all on Wednesday.
Thank you.
I'll try to be a little more on top of my variables and on top of my game.
Oh yeah, so could I take this standard quiz before class on Wednesday then?
Yeah, that's okay. Yeah, that's fine.
Okay, thank you.
2/2. What are you saying has to be 2? 2/2? Oh yeah, no, that's 2. Oh, sorry, this isn't referring to the numerator specifically, this is referring to the fraction as a whole. So what I'm saying is if you take n squared plus 1 all over n squared, 2n squared, you can actually write that if you split it up into 2 fractions. Like that.
Okay.
And then it turns out that's just a half plus 1 over 2n squared. And so then the sequence b sub n as a whole, you can say that b sub n is going to converge to a half plus 0, because this goes to 0. And so the overall sequence is converging to a half. Yeah, not the numerator or anything of this expression right here. This means, this is referring to the sequence as a whole is converging to a half.
Okay, I think that sort of makes sense. I'll try to be in for office hours. I'll try for tomorrow for that one.
Okay, sounds good. Hey Joy, what's up? Oops, sorry, I just realized I need to actually end the video.